All right, so we're back. And to recap where we left off, you now have this new capability in code to do pointer arithmetic, like treat addresses as numbers, which they really are in hexadecimal or otherwise, and like add them together and kind of poke around a computer's memory. And it was asked during break, actually, how we might further harness this in the context of strings. So I didn't change the code we wrote just before break. Recall that we last broke the program by checking out bytes 50,000 bytes away. But let's not do that, and let's actually try printing out not individual characters like I did per the %c, but why don't we try printing out strings and substrings, if you will. So let me clear my terminal window. Let me change all of these %c's to %s, 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 and then let me rewind to what we've been doing since week 1 with strings, which is just print them out. For instance, with that first line. And the only difference at the moment is that now I took off the training wheels. I got rid of cs50.h, wherein string is typedef to char star for you. Got rid of that. So now on line 5, I'm declaring s as being a char star, which just means the address of a character. And printf is smart enough to know that the end of a string is wherever that null character is. But now that I can do pointer arithmetic, notice that I could do something like this. If I want to print out s, I just print out s. Suppose I do s plus 1 here and s plus 2 here, again after changing %c to %s. Any intuition around what this code will now print on the screen, line by line? Yeah, thoughts? OK, reasonable conjecture. Maybe the memory address of h, that of I, that of exclamation point. But other thoughts? Yeah, I think it's actually going to do the latter. It's going to print hi in the usual way, because honestly, line 5 is this, rather, line 6 is the same as like week 1 stuff, except we took off the training wheel of string and we're calling it char star. But I think line 7 is indeed going to print out I, and line 8 is just going to print out because it'll be just the exclamation point. Printf will still be smart enough to know where each of those substrings, portions of the string, end by the same logic as always. But let me go ahead and zoom out, run make addresses, enter, compiles OK, /addresses, and now, indeed, this is all a string is. It's a sequence of characters identified by its first byte. If you then start poking around and tell printf to print at what's at the next byte or the next byte, it's going to do its same thing, printing out that character and everything after it up until that null character. So again, even though there's like a lot going on, we've introduced these 2 new operators, like there's nothing that's happening today that hasn't been happening for weeks, but hopefully through this week, this week's lecture, this week's problem set and beyond, you'll start to realize that now you just have more tools via which to harness those lower level implementation details. So last week too, recall one other implementation detail. I claimed that you could not compare 2 strings quite as easily as you could compare to integers, for instance. And I told you to use a different function instead that you probably used 1 or more times with the past problem set. How are you supposed to compare strings, apparently? Yeah, so string compare, strcomp, that additional function that we said, you just have to use it for now. But you might have a little intuition already as to like why we have to use strcompare and we can't just use equals equals to compare strings. Like any intuition for this already? Why was strcompare necessary last week? Perfect. Equals equals would compare literally the 2 memory addresses instead of the actual strings character by character. And unless the memory addresses are literally the same, so you compare that exact same memory address, 2 different strings probably are not going to be considered equal, even if to us humans they indeed look equal. So let's see this. Let me go ahead and close addresses.c. And actually, before I do one last mention, one of the powerful things about pointer arithmetic, as an aside, is that C, and really the compiler, is smart enough to know how many bytes to keep adding and adding. And by that I mean this. Right now we got lucky because a string is a sequence of characters. And by definition, every character is a single byte. You can poke around and do s plus 1 to get the next byte, s plus 2 to get the 3rd byte. However, if we weren't dealing with strings, suppose we were dealing with integers that were in an array back to back to back. If you wanted to get at the next integer, you could still do +1 or +2 to get at the next or the next integer. You would not start to get into the weeds of doing +4 and then +8. You don't have to know or care how big the data types are in the computer. C in the compiler will figure that out for you based on the data type in question. So keep that in mind if ever doing this on a different data type than chars. All right, so let me go ahead and open up a file that I wrote in advance most of. And let me hide my terminal window and show you this. So here's a program called compare.c, whose purpose in life is to compare two strings. I'm back to using the cs50 library because at least for now and probably a couple more weeks, it is so much easier to get input from the user using cs50's function, getInt. But we'll conclude today by taking off those training wheels as well so you can see how you can actually get user input with nothing cs50 specific. So lines 6 and 7. Pretty boring, week 1 stuff. Get an int called I, get an int called j, and store them in two variables, I and j respectively. If I equals j, print out the same, else print out that they're different. Let me just stipulate for time's sake, I'm pretty sure this code is correct. This will get two integers from the human. It will compare them and tell me correctly if they're the same or different. And I'll prove as much by running make compare /compare, and I'll type in 50 for I, 50 for j, and they're the same. And now I'll do how about 50 and say 13, and those are different. So let me just stipulate this code is indeed correct. Would have worked in week 1, also works now in week 4. But let me now change it to compare not to integers, but as I hinted, maybe to strings instead. So let me go ahead and change this line of code to maybe be string s equals get string, asking the user for s. Then let's change this second line here to be string t, just to keep the variable name short for now. And t is a good choice after s for something like this. Get string, prompt the human for t. And then let's change our I and j here to do the wrong thing. Per the intuition earlier, if s equals t, then print out the same, else print out that they're different. Now, if I want, I could take off at least some of the training wheels. I could change this to char star. I could change this to char star. Either is fine. I still need the cs50 library, though, because I'm using get string, because it's actually hard, as we'll see today, to get strings manually without using a library. But I'll keep it using string just for now with the library. All right, make compare again. /compare. And now let me go ahead and type in, for instance, hi, exclamation point, enter, and hi, exclamation point, enter, and they're different. All right, they're obviously not visually, but they are underneath the hood. And you probably do have the intuition for this already, whereby what's going on underneath the hood is that we're comparing accidentally the two memory addresses. So in fact, let's go there. Let's consider the memory. And let me zoom out now so I can just have more bytes to play with. So the squares are a little smaller than before, just so we can fit more in them. And let me propose that when I declare s on what was line 6, a moment ago, it ends up somewhere in memory, like the top left-hand corner of my picture, for discussion's sake. And when I execute that same line of code and get string is called, and I type in hi exclamation point, we know from week 1 that get string puts it somewhere in the computer's memory. And I'll propose that it's in like the bottom left-hand corner of the screen here. What happens after that? Well, I know, even though I don't generally care, that hi exclamation point and the null character exists at some address, like 0x123, 124, 125, 126, for discussion's sake. And what's in s? Same as before break, 0x123. So that's all that's happening again on line 6, which is pretty much the same as when we were getting an s earlier. But notice now with line 7, when I get a second variable called t and I call getString again, and by coincidence, as the human, I type the same thing. Well, what happens here? T gets its own chunk of memory, maybe at the top right. That second version of hi gets somewhere else in memory. You know, the computer could be smart and notice that it's the same, but C doesn't generally do that for you. It just plops it somewhere else in memory. And maybe it's at address 0x456, 457, 458, 459, or wherever. But you can perhaps see where this is going already. T now, of course, contains the address of that first byte. And so in my code on line 9, when I compare S and T for equality, suffice it to say they are not equal. Because of the way the strings are laid out in the computer's memory, it indeed looks the same values are there. But if we abstract away further, you can really see that S and T are not the same themselves. And so how did we fix this? Or really, how did we avoid this last week without spilling the beans and going down this rabbit hole of explaining like why you have to use stir compare? Well, if I go back to my code here, let's do it now the right way. Let me go ahead and include a line of code that says string compare of s comma t, both as inputs, and then if you recall, what does stir compare return when two strings are equal? There's 3 possible return values. So 0. So 1 is for if it comes alphabetically or ASCII-betically first or second. But for now, I just want 0. If I want to use stir compare, I do need string.h. So string.h does exist. That's not a cs50 thing. There's no keyword string as a data type. That's a cs50 thing. But string.h does exist. So I think now, with that change on line 10, if I do make compare and /compare, and then run again, type again, hi, exclamation point, hi, exclamation point, I think now they're the same. And just as a second check, hi in all caps, maybe hi in lowercase, those are in fact different. Why? Well, stir compare, which was written by some other human decades ago, is just smart enough to know that it should go to s and go to t, start comparing them left to right, stopping once it hits one or both null characters, and return 0 only if everything in s and in t are exactly the same. Are any questions then on this here? Any questions on why we're using stir compare? All right, if no, yeah, oh, in the middle. Yeah, so why is it not the case with integers? So it turns out it's not the case with integers, with floats, with bools, with doubles, with longs. Like literally every other data type works correctly. Strings, though, are special. They're useful enough in programming and have been for decades that the authors of printf and the authors of stir compare and bunches of other functions, Sterling for that matter, just kind of treat strings special because they're just useful, right? We humans interact using language, be it English or anything else. And so it's just useful to have into the language C just sort of first-class support for this notion of strings of human text. So the short answer is just because. Like it just is necessary. Strings are different. They're implemented with this address and the null character. Everything else, though, is just a value. But a string, again, is a white lie. It's an address. It's not a thing unto itself. Good question. Yeah, in front. Oh, really good question. So in my code here, in VS Code, what if I do this? Instead of stir compare, and instead of if s equals t, what if I start playing around using star s and star t? Really interesting case to consider. Let's go back to our sort of deductive logic here. So star, the asterisk operator today, means go there. So when I've typed in hi once and then hi again, both uppercase, for instance, what is at the address s literally? Someone else. What is at the address s? Yeah. So not quite. At the address. So not what is the address. What is at the address 0x123? H. And what is at the address 0x456? H also. And so here, you're kind of cheating. Like you're comparing the first character of both strings, but not every other one. Now, you could be really pedantic. And here, again, this is not like a good use of code. But you could do this. If that, and how about this craziness? So star s plus 1 equals star t plus 1. And you could do this for every character manually. But that's why stir compare exists. It does all of this for you. But that's why. And that's the intuition. So I would encourage you to, anytime there's something kind of weird going on, I realize we might be straining credibility now. We haven't told you that many white lies. And so most everything that we've seen thus far can explain pretty much all of the behavior up until now from week 1 onward in C. So let me revert this back to the right way. If stir compare of s and t equals 0, this now is the right version of the code. And now here is again where you can play. So let me do this. Let me clear my terminal window just to tidy things up. Let me get rid of all of this comparison stuff. And let's just see what's going on. As you are welcome to in your own code, let's print out, for instance, as we might have in week 1, the value of s itself in a new line, comma s, and then let's just print out t just to make sure it compiles and I'm not doing anything wrong. But this is not going to be that interesting. And frankly, I don't need string.h anymore because I'm not using stir compare. So make addresses, /addresses. There's my, oh, sorry, that's fun. OK, not %t, %s here too. Ignore that. Let's do this again. Make address, oh, and that's the wrong program. OK, let's do make compare. /compare, and let's type in hi again, and now we just see the two strings. I'm not comparing. But now we can kind of play around, right? Instead of printing out %s, which prints the string, how do I print the address in S? I just need to make a slight change. If I want to see not what's at S, but I want to see S, the address. Yeah. Perfect. So change %s in both places here to %p. So now printf will treat it literally as an address. It's not going to do any fanciness with a loop from left to right looking for the null character. It's just going to print out s and t. So let me clear my terminal, run make compare. Whoops. Let's do make compare, /compare, enter, type in hi again, and now you see, oh, so this is interesting. It's not quite as straightforward as the other values, which were one byte away. They're almost the same, but this one ends in B0, this one ends in F0. So they're indeed separated by some number of bytes. Not just one, but a few, because these strings are indeed longer. All right, so once you've seen this here, how can we now maybe leverage this to solve other problems? Well, let me propose that we do this. Let me zoom out here. Let me close compare. And let me open up another program I wrote part of in advance called copy.c. So copy.c, in theory, makes a copy of a string. How? On line 8, I'm using the same thing as before, get string, storing it in a string or char star, and asking the user for it. Then I'm not asking get string again. I'm just making a copy super simply with line 10 here, string t equals s. Now, intuitively, I think that's how I would copy a variable, right? That's how we've copied variables every week thus far in C. But something's going to go wrong. In line 12, in English, does someone want to explain what you think line 12 does? Don't worry about finding any bugs or mistakes. But what does line 12 seem to be doing using toUpper, which is thanks to the C-type library, which I've included the header file for? Yeah. Yeah, right? It's kind of like ugly syntax, but this would seem to be capitalizing the first letter of t specifically and just changing it. So we have t bracket 0 here because we want to save the change, and we're passing to toUpper the first character here. So this is how we did uppercase in the past, and now I print out s and t respectively using %s. So this feels like it should work. I copied s and stored it in t on line 10, and then I change t and only t on line 12. But you can perhaps, if you're comfy thus far, see where this is going if I do make copy, /copy, and let me type in lowercase hi, exclamation point this time, just once. So I'm going to hit enter, and watch what we see for the value of s and t. Huh. The new value of s and t at the end of my program seems to be what? It seems to be the same. Hi is capitalized both times. So what's the intuition then for this? Why did this just happen? Yeah, and back. Yeah, I assigned s and t the same memory address. So it did copy s into t, but C takes this very literally. What is s? It's an address. What is t? It's a copy of that address. If you want to copy the whole string like a normal human would expect, hey, you or someone has to do a lot more work. You have to go to that address, copy this character, this one, this one, this one, and copy it to a new location in memory. That does not happen automatically here for you in C. It does in some other languages. Those of you who've programmed in certain higher level languages, this just works as you would hope, and that's one of the benefits of Python and other languages that we'll soon see. But for now, it literally takes at face value what this is. Copy the address into this address. And I'll make that more clear by getting rid of the string keyword, which again is just a type def. This is technically an address here. This is technically an address here. So what's being copied is the value of that address, not all of the characters that might very well follow it. So I should make one note too here. I'm going to start getting more in the habit of trying to avoid segmentation faults because things could go wrong here. For instance, on line 12 previously, I was kind of blindly, naively, dangerously assuming that there will be at least one character in S or T. That might not be the case. If the user just hits enter, there's no characters to uppercase. And so this is reckless of me and could theoretically create a seg fault. So I should probably start to be smarter and say something like this. If the length of t is greater than 0, OK, now it's safe to actually capitalize the first letter. And that will decrease the probability now of those segmentation faults by just not making any assumptions about what the human does. Almost always, your programs will crash when you've made a mistake, yes, but the user gives you an input that you yourself did not expect. So what does this all look like in memory? Well, let's go back to the big grid. this time focusing on the copying of values. And let's do this. Here's s, as in this new program, just declared to be a char star. Here is where my lowercase hi maybe ended up in the computer's memory. That's probably at 0x123, 124, 125, whatever, something like that. And that's, of course, what ends up in s as a value. When I declare t, I do get a second variable called t, just like before. But when I copy s into t, what happens? It's really just literally 0x123. Whatever the value of s is now also the value of t. And so if we abstract this away at a high level, get rid of all of those extra squares, this is what s and t now are. They're indeed copies, but copies of each other, not copies of the underlying characters. And so if you follow those arrows and try to print them both out after capitalizing one or the other, you're going to unfortunately end up capitalizing not just one of them, s, but both of them, s and t, because literally it's the same address. Any questions then on this visualization? Yeah. Good question. Is this pass by reference? We have not seen in detail an example like that. Right now, you're copying by value. But references will come into play. And remind me in a bit if I haven't used that term yet. But this is just copying things by, could have ended poorly, value. Other questions? No? All right, so with this in mind, like how do we actually copy things properly? For this, we actually need another building block. So today we give you two functions, one of which is called malloc, one of which is called free. And these are used all of the time by like every piece of software you and I use on our Macs, PCs, and phones, whether it's written in C or some equivalent other language. Malloc is for memory allocation. It's a function that you can use to ask the operating system, Mac OS, Linux, Windows, anything, for some number of bytes. 1 byte, 100 bytes, a gigabyte of memory. You can ask malloc for however much memory you want in advance. It will return to you the address of the first byte of memory that it found free for you. Unlike a string, it is not null terminated. And so the danger with malloc is that it's on the honor system. If you ask it for 1 byte or 10 bytes, you, the programmer, in like a variable, have to remember how many bytes you requested, 1 or 10 or the like. Strings do that for you, not when we're getting now to this low level. Malloc's just going to give you some memory, and it's up to you to manage it. Free does the opposite. When you're done with some chunk of memory, you can free it by passing in that same address and just hand it back to Mac OS, Windows, or Linux and say, I'm done with this. You can let me use this for something else later. As an aside, if your computer has ever like frozen or hung, like the whole thing maybe just spontaneously reboots, yet another reason for a bug like that might be if you write a program with a bug that keeps mallocing, that is asking for more and more and more memory, but you make a mistake and you never free it, well, eventually the computer is going to literally run out of memory and something's going to go wrong, and that's often when computers freeze. Like they're just out of memory. It has the memory there, but the program was trying to use too much of it endlessly. So this too will be a mistake that some of us will surely make in the coming weeks, but hopefully you'll now see the solution. So let me go back to VS Code here, and let me propose that we do the following. I'll hide my terminal window for a moment, and I'm going to introduce another header file up here. And I promise there's not going to be too many more of these, but this one is called standardlib.h for standard library. And in this file are the declarations, the prototypes for malloc and free and a bunch of other stuff as well. It lets me now manage my own memory. So let's focus now on line 11. Line 11 is where I went wrong before, because conceptually I want to copy the whole string, but of course I'm only copying modestly the individual address. So how do I copy the whole darn thing? Well, what I need to do is this. When I declare t to be the address of something in memory, why don't I set t to be the address of a free chunk of memory? So let me ask the operating system, give me this many bytes, tell me what the address is, and I'm going to store that in t initially, just so I know where there's free space for me. So how do I do that? Well, quite simply, I call malloc, and then I pass in the number of bytes that I need. Now, for hi exclamation point, I think I need 3, although wait, no, I really need 4 because of the null character. But I don't think I should be hard coding numbers like this, because who knows what the human's going to type in. So I can actually use strling of s and then +1. This will ask malloc then for however many bytes corresponds to the number of characters the human typed in, +1 for, again, the null character. So it's just being smart and defensive rather than choosing a number myself. But now all t is a pointer, if you will, to some random chunk of free space. So there's nothing there yet, or there's bits there, but who knows what value they are. They're certainly not identical to what the human typed in. I now have to do this. So how can I copy one string into the other? Well, let me do this. Instead of capitalizing something just yet, let me do this. How about for int I gets 0, I is less than the length of s, and then I plus plus. So I'm going to iterate for the whole length of the string. And in here, I'm just going to do this. The ith character in t should be identical to the ith character in s. So I'm just literally copying from right to left each and every character in s. And I can trust that there's enough memory in ty because I asked for that many bytes plus 1. Now, there's technically a bug here. I actually should probably do this. I should do plus 1 here. Or, if you prefer, I should do less than or equal to the strlang. But I think it's a little clearer to do the plus 1. Why do I, for the first time, want to go just beyond the boundary of s and copy one more byte? Yeah, I need the null character. Like, I could technically manually add it with some additional line of code, but I might as well just copy it because \0 is \0. So this time, and probably only this time, it's reasonable and correct to go just beyond the boundary of your string. So you copy the null terminating character so that the computer also knows where t ends. And now I think what I can do a little more safely is this. Let me go down here and say t bracket 0 equals 2 upper of t bracket 0. So same line of code as before. If I actually want to be really safe, I should probably do this. So if the strlang of t is greater than 0, so there's at least 1 byte there, OK, now it's safe to blindly capitalize the first character. And I think that now puts me in better shape. So let me try this now. Let me open up my terminal, make copy, /copy. I'm going to type in hi exclamation point in all lowercase, crossing my fingers this time. And now if I zoom in, it indeed capitalized only t and not s in this case. So pictorially, let me switch over here. Here is, as before, the variable s pointing at hi in all lowercase. When I call malloc, though, that gives me a chunk of memory that I'm going to store the address in t of. So if t is some other variable, as it is in my code, and there's some other available chunk of memory, I don't know where it is, but let's assume, as always, it's at 0x456, 457, 458, 459, so 4 bytes total. What is now happening? Well, t is defined as pointing to that, because that's what malloc gives us, the address of the first byte of the free memory. And now with my for loop, I'm just iterating over it, copying the h, then the I, then the exclamation point, and then for good measure, the \0 instead. Questions then on this process here? Yeah, and back. A really good question. If I omitted in my code the +1 and I didn't do less than or equal to, so that I'm copying the 4th byte, odds are in this program, because it's so short, you wouldn't notice that there's an actual error. But what could happen is, when I call printf on t, if there's no null byte there, it might print h, I, exclamation point, some random value, some random value, some random value, some random value, until it gets lucky and there happens to be a 0 byte, a null byte by chance, for instance. So if you don't include the \0 some way, that's going to happen. And I say some way, I could even do this. I could technically just copy the length of the string s, and at the very bottom here, I could do something like t bracket strlang of t. I could do this, but this is just not necessary. Like, I could manually add it at the end of the string. But again, I'd claim that it's just simpler to borrow, that is, copy the one that's already in s, because it's the same thing at the end of the day. Good question. Other questions on this copying correctly now? Other questions? All right, is there any room for improvement here? Well, let me propose a slight optimization. This is kind of a throwback now to week 1. Turns out that arguably my line 13 here, wherein I have this for loop, now that I'm doing things in loops again and again and using a function like strlang, this is correct. It will iterate from 0 on up to the length of s plus 1. But it's kind of stupid of me to write this for loop in this way. Why? Well, here's my initialization on the left. Here's my condition in the middle. And in general, calling a function inside of your condition is probably not very good design. Like, why? Why is it bad for me to be calling a function like Stirling in this condition in the middle of my for loop? Yeah. Yeah, you're just calling it again and again for no reason. Like, the length of s never changes. So, like, why are you wasting everyone's time by calling Stirling of s again, 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 just to check this inequality, whether I is less than that value? So it turns out, if you haven't discovered this already, there's a slight optimization we can do here that has nothing to do fundamentally with strings or pointers, just with better design. I can actually define two variables at once. I could do this. Let me remove this whole condition. And let me add a comma after I equals 0, set n, or any variable, equal to the Stirling of s plus 1, and then after the semicolon, just ask the question while I is less than n. So it's almost the same, but notice now my condition in the very middle of this loop is at least comparing two static values. N never changes. Sorry, one static value. N never changes. All that changes is I. But I'm not foolishly calling Stirling, Stirling, Stirling again and again. Why? Well, how does Stirling work? Similar in spirit to printf, Stirling, given the name of a string, looks at the first character and then starts looking through the entire string, looking for the null character. And we saw this in week 2, counting up how many characters are there. So it's just a waste of time again and again.
Do you have to find n all the way at the top so that way you use n again in the
Totally. If you wanted to use n multiple times, you could absolutely take it out of the for loop, put it right after s is defined, and reuse n and again and again. Absolutely. But in general, consider this when designing your for loops. Even though modern compilers like Clang can actually fix this problem, this inefficiency for you, good practice would be don't call functions unnecessarily, especially if the answer is always going to be the same. All right, so what else should I perhaps refine here? Well, how about I do one last thing and just comment on what exactly could go wrong here? Well, a couple of things. Well, actually, this is just silly too. Like, surely someone before me in the world has had to copy a string before. Surely there's a function like called strcopy, maybe, like strcompare, like Stirling. And indeed there is. So let me propose that we actually get rid of this whole for loop, and we actually just call a function called strcopy, no o, just strcpy, and pass in the destination, which is t first, and then the source that you want to copy into the destination, and that takes the place entirely of that whole loop. So again, I demonstrated the loop first just to be very pedantic about it, but that's wasting time. You're wasting time writing lines of code you don't need to. Strcopy is what you can use here instead. And so this has now always existed. And what more can I do? Well, as one final point, it turns out that there's actually things that can go wrong in this code, even besides the string being too short. Like if the human just hits enter and there are no characters, I don't want to blindly capitalize the first character that doesn't exist. That's why I added that if condition. But there's other things that can go wrong, and we introduced those to you today. It turns out that functions like getString and functions like malloc return potentially a special value. And wonderfully confusingly, it's also called null, but with two L's. All right, so left hand and right hand weren't talking so well like decades ago. NUL is a \0. It's a single character, as it always has been for a couple of weeks now. NULL is technically a pointer. It's an address, but it's address 0. It's like the top left-hand corner, if you will, of your computer's memory that just nothing is ever supposed to go in by convention. So null is a synonym for 0, but it's specifically an address. Now, why is this useful? Well, suppose that in my code here, something goes wrong with getString. Suppose you're being a little crazy and you type in way too long of a string. It's not just hi, but it's like an entire essay of text, and there's not enough memory in the computer. How does getString signal to the programmer, whoa, like that's way too big of a string. I can't fit it in memory. Well, we never told you this, but all of this time, it turns out that getString will return this special value called null if something goes wrong. So to be really careful now, you should do something like this. If s equals literally null, then you better exit the program entirely and return like 1 or 2 or 3 to signify that something went wrong. Don't go any further. Similarly with malloc. It's possible if you ask for way too much memory, that could fail, especially if you're asking now for double the memory after the human types something in. So if t equals null, then you know what? Let's also return 1 or some other value to just get out before something crashes or freezes on the human as well. So honestly, I tend not to do this always in class because the code just gets so bloated and complicated. But you absolutely, in practice, need to start doing this. Otherwise, you will be responsible for the freezes and the crashes and the reboots that users in the real world might actually encounter otherwise. Of course, if we get to the bottom of this program now, I should probably return 0 explicitly or implicitly to just signify that everything is successful. But there's one other thing I haven't done. We introduced malloc, but what did I claim also existed? So free. I'm also being a little reckless now. Here I am not practicing what I'm preaching. I'm asking the computer for memory via getString. I'm asking the computer for more memory via malloc, and I'm never technically handing it back. So really what I should be doing at the very bottom of my program too is freeing the memory I've asked for. So henceforth, it is a rule, a law, if you will, in C. Whenever you allocate memory with malloc, or certain other functions as well, you, the programmer, must free it when you're all done with it. Now, this is a bit of an overstatement because technically when programs quit, they'll free the memory automatically. So you're not going to break someone's Mac or PC because you necessarily have this bug. But for programs that are running all the time, like someone keeps a Chrome, their browser open, Microsoft Word or the like, bad things will happen if over time you never call free and the program keeps running. So always get into this habit here. You do not need to free memory that comes from getString because the cs50 library automatically frees it for you. But you, anytime you use malloc, henceforth, as you did or I did here, you must free that by just passing in the same address you got back. Questions now on malloc and free? Questions? Yeah? A really good question. So free so what does free do? So free just lets the computer know that you are done with that chunk of memory, which means that if you have another line of code elsewhere, that same memory might be reused and can be used again and again. And that's going to be necessary, certainly for any long-running program. You can't ask for memory constantly. You'll eventually run out. So you need to free it in this way. Other languages, as an aside, Python, yet another motivation in a couple of weeks for it is going to be Python and certain other languages manage all this headache for you. But in C, the goal here is to really harness these capabilities ourselves. All right, so it turns out like almost everyone in the room, myself included, you're going to screw up when it comes to anything memory related if you haven't already. Seg faults are in your future, but hopefully there's tools via which you can detect these things and fix them proactively and not just use printf or debug 50 or rubber duck. We actually have another tool we can equip you with now that'll help you find some mistakes. So let me do this. Let me close copy.c. Let me open a program I wrote in advance called memory.c that doesn't do anything really interesting, but it's going to have 2 bugs in it. Notice that I've included standard.io.h, as always. I've also included standard lib.h, which is necessary now for anything related to malloc and or free and the like. Line 6. It's a little weird what I've done here, but this is like the manual way of asking for enough memory for an array. In week 2, how do we ask for memory for an array? You very simply say int x3, and that gives you an array called x of size 3. But if you do it manually now using malloc, what you have to do is use syntax like this. You call malloc, you ask for 3 things, times however big an int is. Now we know it's 4, so you could literally write 12 here, but this is more generic. So 3 times the size of an integer will give you 12 dynamically. And what does malloc return? The address of the first byte you get back. What do I want to put that? Well, I want to put it in a variable. Now the variable can't just be int x, because that's a number. It's not an address per se. If I want to store this address in a variable, I could call it x, I could call it p. But int star x just means that x is now the address of a chunk of memory. Specifically, a chunk of memory that's big enough, not for 1, but for 3 ints in total. All right, now I'm just sort of naively putting our old friends 72, 73, and 33 at the first, second, and third locations in memory. But perhaps based on week 2 or week 4, I'm clearly screwing up here in a couple of ways. Someone want to identify at least one bug. What did I do wrong? Yeah, like this is now, amateur stuff. Like I should be 0 indexing, not 1 indexing. So this has got to be 0, 1, 2 ultimately. And other bugs that are maybe more week 4 specific? Other bugs. It's more subtle. Yeah. I'm not freeing the memory, right? So I'm not practicing what I'm preaching by freeing this memory. Now, suppose these are non-obvious. And honestly, after like an hour or two of this, like this shouldn't be obvious yet. It will be over time. How could I find these bugs with software as opposed to just staring at the thing or asking someone for help? Well, let me propose this. Let me first go ahead and run make memory to compile the program. And it seems to look fine. There's no syntax errors, at least. /memory, notice, seems to work fine, too. Now, this program doesn't do anything interesting. There's no printf or anything like that. But it didn't crash. There's no segmentation fault. But that doesn't mean there aren't bugs latent in the software. And this is true, sadly, of all of today's software, like Chrome and Microsoft Word and other programs surely have memory-related bugs that people at Google and Microsoft haven't yet found. But there are tools, at least to find the most obvious of those bugs. And we're going to introduce you now to a program called Valgrind. So Valgrind, it's a fairly fancy program, but we'll use it for very simple ways. We'll look at your code and find memory errors as it's executing and try to help you understand where they are. So let me go back to VS Code here. Memory seems to be fine. You know, I feel like, OK, I'm going to submit this homework. All is good. No error messages. That's no longer the case. Now you need to poke a little more at your code to see if maybe there's still some bug there. So let me do this. Valgrind. And then space /memory. So just like debug 50, you run it on a program you already compiled. Valgrind, I'm going to run it on a program I already compiled. Let me zoom in on my terminal window so we can see more at once, and enter. All right, the output is crazy cryptic for no good reason. There's lots of numbers and equal signs. It's a lot of clutter, but there is some juicy information here. And let me start from the top down. Invalid write of size 4. So write means to change a value. Read means to like access a value. And this is, again, esoteric like a lot of our error messages are. But it looks like after a block of size 12 allocked, and then there's these weird hex notation. There's some mention of malloc. But honestly, the juicy part here is memory.c, line 6. That's probably my fault. So let's look at line 6 per that output. Let me shrink the terminal window. Look at line 6. OK, 12 is now germane, right? If you did the mental math of the size of an int times 3, 12 is somehow involved here. But line 6 is now happening next here. That's where the memory came from. What is this? Let me zoom back in. Where is there invalid write of size 4? Like, what's perhaps going wrong here? Invalid write of size 4. What does that mean? It's like a very technical way of explaining. The bug is actually one line later on line 7, as we already identified. Yeah?
When you call x3, you are calling the fourth position of that integer. So I guess that doesn't match the memory you asked because you asked for 3.
Think through deductively, like, what could that mean? But I'm clearly touching 4 bytes of memory in these few lines of code that I shouldn't be. And hopefully here, as the light bulb already went off earlier, oh, I'm not 0 indexing. OK, that must mean that x bracket 3, as you note, is just too far past the chunk of memory. So I'm invalidly writing to 4 bytes that I shouldn't be. So again, it's not super obvious. This is not super user-friendly. But at least it does give you a clue as to where that bug is. So the fix there is going to be quite simply to change the 1 to a 0, the 2 to a 1, and the 3 to a 2. That'll fix that. But there's still a second error. And let me look at the cryptic output again. Heap summary, some stuff there. OK, this does not sound good down here. 12 bytes in one blocks are definitely lost in loss record 1 of 1. Very arcane output 2, but clearly related to line 6 again, our allocation of memory. Now here too, it's not obvious what the solution is, but memory is lost, AKA this is a memory leak. And now the deduction's kind of up to you. What is leaking? Oh, wait, I didn't call free. And so the second solution here is probably to free x at the very end of the program. And if you really want to be pedantic, you should probably check, like I proposed earlier, if x is null, just get out now while you still can, and don't even touch those other lines of code. But if you get to the bottom, return 0. But really, the takeaways are, I fixed my 0 indexing of the array to avoid the invalid write of size 4. And now I'm freeing the memory that I asked for. So there should be no leak lost. All right, let's try this again. Make memory, /memory. No visible errors yet. But let me now increase my terminal window again. Do valgrind of /memory, crossing my fingers. And now all heap blocks were freed. No leaks are possible. I don't see any invalid writes. There's still a crazy amount of output. But none of it is erroneous. It's not bad. Now I've fixed my memory bugs. And so now my TA, my TF, they're not going to find them either, because at least Valgrind has proactively done that for me. Questions then on Valgrind? Generally, it's those two types of errors you might trip over. There's not too much else in the way of arcane output. Questions then on this? No? All right. Well, what else might be going on? So someone alluded to this earlier. What happens when you, for instance, forget the null terminator? Or you generally start poking around memory that you yourself didn't ask for, or looking at values you didn't put there? Well, let me go ahead and open this. Code of garbage.c, in honor of Oscar the Grouch here of sorts. And here is a simple program. If I hide my terminal window, that just does something kind of arbitrary. I first declare an array called scores. But I made it crazy big, like 1024. Like, that's a lot of integers, but so be it. And then I iterate over those integers, and I print each of those scores out. So I'm using week 2 syntax here. But based on this program, what have I clearly not done that I did do back in week 2? I've allocated the array. I'm printing the array, but. Yeah, I didn't initialize any values for that array. Back in week 2, we didn't do 1024. We did like 3, and I typed in like 3 test scores or something like that. Here, I'm allocating memory, even more than that, just because I really want to be dramatic with what I'm demonstrating. But I'm not initializing those values to anything. And so here it turns out in C, generally, if you do not initialize a variable, or you do not initialize an array with explicit values, there are going to be garbage values there, so to speak. Remnants of that memory having been used before, probably by some other function of yours, some library function, or something else while your program is running. Not a huge deal with a super small program like this, but for anything sizable, memory is going to be used and unused and used and unused. That is mallocked and freed again and again. There's going to be lots of garbage values in the computer's memory by default. So if I open my terminal window here, let me do make garbage. Let me zoom in on my terminal so we can see the output. When I run /garbage, theoretically, I should see 1,024 integers, but none of which have been initialized. Now, I'm going to get lucky with some of them. And it looks like, wow, OK, a lot of them are initialized to 0. And C does, in some contexts, initialize memory for you to 0, at least at the beginning, but not again and again, typically. But if I start scrolling backwards in time at this array of size 1024, where did these values come from? So just random positive and negative numbers interspersed among the zeros? Well, that's because I'm literally poking around on a random 1,024 bytes of the computer's memory. Who knows what's there? So the lesson here is that garbage values are indeed this like term of art. It means that a variable that you might have defined, that you might have declared, if you don't give it an explicit value, who knows what's going to be there? And the lesson here is just don't do that. Always initialize variables to something, either yourself or prompting the human for it. Questions about garbage values? You'll see them sometimes if you print things you shouldn't or touch arrays beyond their boundaries. All right, so maybe to make this a little visual too, it turns out that a lot of things can go wrong, unfortunately, with pointers. And we've seen some of them. And here's another program that's a little contrived. It's very simple. And it just is about manipulating values. It doesn't do anything useful per se, except demonstrate some of today's concepts. So in main here, let me propose that we declare a pointer called x that's going to store eventually the address of an integer, apparently. Here's another one called y that's going to store the address of an integer as well. Here now, I'm allocating enough memory to fit one integer. Now, technically, it's 4. We know that. But size of int just gives me that answer dynamically. So it will work on all systems. And I'm going to store the address that malloc finds for me in x. Then I go to x and put the number 42 there. All right, y, it's the sort of meaning of life, the universe, and everything here. But star x, again, just means go to that address and put a value there. So y, I don't know, but it's just correct at this point. But what about this line here? Star y equals 13. Unlucky in this case. What's bad about this line here, star y? It's a combination now of today's primitives and that point here. Yeah? Yeah, we didn't ask the computer to allocate any space. So y was not initialized with an equal sign at any point to anything. And so what is inside y, so to speak? Like a garbage value. Maybe it's 0, which isn't bad because at least it's nice and simple. But maybe it's some crazy large positive number, some crazy large negative number. Either way, odds are if I go to this address or that address randomly with star y, bad things are going to happen. And so let me go ahead and propose, well, let's not do that. Let's actually do this instead. In line, the second to last line here, why don't I instead assign y equal to x? And we've done that before. And then I can go to y now and change what was a 42 to a 13. Again, why? This is just for educational sake. But for now, this does not crash because I only dereference y with star y after actually giving it a value, albeit a duplicate value, similar to our copy example earlier. So our friends at Stanford have put together a wonderful visual. It's about 2 minutes long. Allow me to dramatically dim the lights if we could and play with what happens with memory when you do bad things like this. I give you Binky from Stanford University.
Hey, Binky, wake up. It's time for pointer fun.
What's that? Learn about pointers? Oh, goody!
Well, to get started, I guess we're going to need a couple pointers.
Okay, this code allocates 2 pointers which can point to integers.
Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything.
That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step.
Oh, right. I knew that. The pointees are separate. So how do you allocate a pointee?
Okay, well, this code allocates a new integer pointee, and this part sets x to point to it.
Hey, that looks better. So make it do something.
Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing.
Your magic wand of dereferencing? That's great.
This is what the code looks like. I'll just set up the number and...
Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y.
Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa!
Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it.
Good point.
Yeah, we allocated the pointer y, but we never set it to point to a pointee.
Very observant.
Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x?
Sure, I'll use my magic wand of...
Did we lose audio?
Is that going to be a problem like before?
No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another.
Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over.
Okay, here goes.
Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13.
Yeah, sharing, whatever. So are we going to switch places now?
Oh, look, we're out of time.
But...
All right, so our thanks to Professor Nick Parlante of Stanford for spending a huge amount of time doing stop motion animation for that. But hopefully now you have a sense of what too can go wrong when you misuse memory in this way. But at the end of the day, we really only have these 4 new building blocks today, like the star operator, the ampersand operator, malloc, and free. And really with that and the underlying understanding of what your computer is doing underneath the hood, we have this way now to really manipulate things in memory, for better or for worse, and eventually we'll see how we can build things. But we can also now use today's primitives to better explain some things that we've been asking you to take for granted over the past several weeks. So for instance, let me propose that we do a one volunteer up here if we could. Could we get one volunteer who's just, you want to come straight up? Yep, right in the middle. Come on. You'll have to take a left or a right there. All right, so we have 2 empty glasses here and 2 colors of liquid. And we have, let me give you the mic, if you'd like to say hello to the group.
Hello, I'm Owen. I'm in Thayer and first year.
All right, welcome. Well, welcome here. I'm going to go ahead and fill these 2 glasses with this colored liquid, purple here on my right. Let's fill up a glass here. Yes, don't drink. And now we'll put some orange in here. And what we'd like you to do for the audience, if you don't mind, is swap the 2 values. We've got a purple value and an orange value, and I'd like the purple liquid in this glass and the orange liquid in that glass, please.
Can I have another glass?
Oh, OK, good intuition, but for the microphone.
Can I have another glass?
So you can, and just in fact, I brought one here for you. Why are you asking for this, though?
Because if I just pour this into this, then it'll get mixed up.
Right, so obviously we need like a temporary variable, if you will. So here's your temporary variable.
And you want, okay.
Yeah, yeah. All right, so pouring the value of the orange glass into this temporary variable, if you will. All right, and now pouring the value of the purple glass into the former orange glass. And now the temporary value goes back into the original purple glass. And now I think we give you a round of applause for having done that very well. Thank you. All right, so it should go without saying that in the real world, like that's how you do this. And in fact, in code, that's pretty much how you have to do this. Although, ask us sometime for a super fancy way of doing it without a temporary variable. Turns out that is possible using bits. But for now, let's suppose that indeed this demonstrates what is the reality in code. If you want to swap two values, you need to have something like a temporary variable. So for instance, on the screen here is the beginning of a function called swap, whose purpose in life is to, as you just did, swap two values, call it a and b. So orange and purple, respectively, are now just a and b in integers to keep things simple. Well, here is the corresponding code, if I may, to what you just enacted as a human. You declared a temporary variable. I'll call temp in this case, which was like me handing you the empty glass, and you stored the orange liquid in it, aka A. You then changed the value of the formerly orange glass to be equal to the purple by pouring one into the other, and then you did the opposite there. Now, at the end of this, you still have a temporary variable that's now empty, so it's temporary in literally that sense. Like, you just don't need it anymore, but it was necessary along the way. So I dare say this code is correct logically. Like, this will swap two values, a and b, thanks to the use of that temporary variable. Unfortunately, though, if I actually do this in practice, let me go over to VS Code here and open a program I wrote in advance called swap.c, which does this as follows. In here, notice I have my prototype for a swap function at the very top. And let me scroll down to the very bottom. There's that exact same code. So I'm the same code for swapping two values, a and b, which I'm claiming for now is correct. Now, if I go back up here, what is main going to do for us? Main is really just meant to be a demonstration of the correctness of your algorithm. So here I declare on line 7 and 8 two variables, x and y, being 1 and 2 arbitrarily, respectively. I then on line 10 just print out what the value of x is and y is, just so I can see it on the screen. I then call the swap function on line 11, and then I literally print the exact same thing again. I print x and y. Hopefully, it'll obviously be the opposite. So I think logically swap is indeed correct. Let me do make swap and then /swap. And I should see x is 1, y is 2. And then hopefully x is 2, y is 1. Enter. But I don't. And it did work in the sense that the code compiled, the code ran. So it's not like some bug in that sense. But because I don't quite understand what's going on underneath the hood, at least as of right now or prior weeks, this code here is indeed buggy in some way. But does anyone have an intuition, perhaps based on today's discussion, as to like why this code, while logically correct, clearly works in reality, apparently does not work in C? Any intuition? Yeah. Perfect. And to summarize, here's that term of art I promised. When you call a function and pass in two arguments, like a and b, you're passing those arguments by value. So copies of those values effectively. And so when swap is actually called here, when you pass in x and y, we call them a and b, but that's just a convention. We could call the parameters anything we want. What a and b are indeed the values of x and y respectively, but copies of the values. So this code here is very successfully in VS Code 2 swapping the values of a and b. But as you note, because I'm passing them in by value, literally 1, literally 2, and not by another term of art, by reference, aka by their addresses, swap has no capability in C to go to those locations, swap the actual locations, just like we did successfully actually in reality. But I think we really have the syntax already for solving this if we consider that really this is just an issue of scope. And we've talked a bit about scope in the past, whereby scope refers to the context in which a variable lives. And generally, I've claimed that a variable exists between the most recent curly braces. And that's pretty much true for the swap function, because a and b, I now claim again, exist only in the context of these curly braces. They have no effect on main up top, which has different variables, x and y. But we can consider now what's really going on underneath the hood. And here's that same picture of memory as we've seen in the past. If we zoom in and see on these little black chips, this is a bunch of bytes of memory. If I create a grid out of it just to kind of highlight that we can address each of these bytes, throw away the plastic circuit board and focus only on those bytes, what's going on underneath the hood when functions are called in C, which you've been doing for weeks now? Well, this rectangle of memory, if we kind of abstract it away further, is generally broken up into different regions or segments, like I called them earlier, and different things get put in different parts of the computer's memory. And without getting too into the weeds, when you double click a program on your Mac or PC, or when you do /something on a Linux, you are loading your machine code into the computer's memory from the computer's hard drive. So all the zeros and ones that compose Microsoft Word or Chrome or whatever are loaded into the computer's memory or RAM. And by convention, it's put up top in the so-called machine code area. And that's how the CPU has access to them quickly at that. Below that are what are going to be our globals, so global variables, which we haven't used very much in C, but you can declare them outside of main at the very top of your files. If you have globals, they end up there as well, just FYI. And then there's this big chunk of memory that we saw Valgren mention indirectly earlier called the heap. And it's kind of like heap, literally, like it's a heap of memory that you can use as you see fit. And the heap is where malloc grabs memory from. So initially, there's nothing in the heap. It's just a big chunk of free space. Anytime you call malloc, malloc kind of carves out from the heap area more and more bytes. And malloc keeps track of essentially which bytes have already been allocated. So initially, it looks empty, but different bytes, squares, if you will, keep getting requested again and again as a program runs, thanks to functions like malloc. And it grows, if you will, conceptually down. So the more and more memory you request for malloc, it starts up here, but then the next chunk you get is down here conceptually. The next chunk is down here, down here. So it kind of fills the available space in the computer's overall memory. But there's this other chunk of memory called the stack. And just like a stack of trays in like Annenberg or a cafeteria kind of grow upward, so does a stack of memory. And it turns out the stack is where functions have variables and have arguments stored temporarily. So whenever you call a function and it has variables inside of it or has arguments there too, this is the chunk of memory in the computer's overall block of memory that are used for functions. But anytime you call malloc, it's memory up here. Right? At the end of the day, they just had to pick a direction, top, bottom, and technically it's an artist rendition. You could circle this thing around any orientation you want, but you're just using a finite amount of memory in this conventional way. Malloc starts here. Functions start here. Now you can kind of see where like bad things can happen. And indeed, one of the other reasons computers can crash is if you ask for way too much memory from the heap by calling malloc many, many, many times, or if you call way too many functions, or accidentally, per last week, you recurse infinitely many times, you might have a segmentation fault. And that's because you're using too much stack memory. So this is bound to be a problem eventually. And the onus is on the programmer to just minimize the probability of doing that and really avoid the possibility of doing that by just checking return values, like checking if malloc or getString return null, because you can proactively with conditionals make sure that these two things do not collide by just making sure that you get back non-null values. So let's consider the stack in the context of swap and what's really happening here. And Carter, if you wouldn't mind helping me animate the screen here, when I call the main function of any program, it is allocated a slice of memory called a frame at the bottom of this stack. So if Carter, you want to go ahead and advance here, here's like the first slice of memory that will always be used by main, whether it has command line arguments or local variables. It just ends up here in memory. Suppose now, per our swap.c program, that main calls swap. Well, where does the memory for swap end up? Like right up here. So swap had two arguments, a and b, and it also had a temporary variable. So all of those end up in here in memory. And if you want to go ahead and advance again, Carter, once swap is done executing, whether it just returns because there's no more lines of code or you explicitly return, this memory is just freed up automatically. You don't call free. You don't undo malloc. This just all happens automatically. It has been since week 1. Now, technically, it's still there, even though we've removed it from the picture. And there's your first hint of garbage values, right? Like, there's still 0s and 1s there, and they're left in the the previous configuration. And so the reason you get random values in the memory is because even though we haven't drawn swap here, there was stuff there a moment ago. It's going to be there the next time you use that same memory. Now, let's go ahead and step through this a little more methodically. Main has 2 variables called x and y, 1 and 2. So let's advance and represent x as 1, y is 2, taking up these 2 chunks of memory. When we call swap now, swap gets a new slice of memory that then gives us 3 variables, a and b, technically the arguments, and temp. So what happens? Well, because functions automatically pass in values by value, or rather pass in arguments by value, x gets copied into a, y gets copied into b, and then once we start executing the algorithm a la the watered glasses, well, what happens here? So if I execute the first line of code, temp equals a, temp gets a copy of a. What happens next? A equals b. So a takes on a copy of b. And now we do the final swap in the glasses. B equals temp. B gets a copy of temp. Now, we don't have to change temp because it's essentially empty, although there's the garbage value. 1 is always now going to be there until we reuse that memory. The important thing, though, is that a and b have been swapped. But what obviously has not been swapped, as is manifest as when swap returns, x and y are untouched because copies thereof were passed in. So we need a solution to this problem. And if we advance one more time, if you don't mind, let me step over here, but then call you back in a second. This code here is logically correct. This is what you did, but this is now a detail of C. You can't just swap the things by value because you're only changing it in the scope of the swap function. But I think if we change it to this and add some annoying syntax, we can solve the problem. Just like you can declare variables as storing addresses, you can declare arguments to functions, aka parameters, as taking addresses. This new version of swap means that a shall be the address of an integer. B shall be the address of an integer. And now it gets a little cryptic here. Temp is the same because it's just an integer like it was in week 1. Nothing special about temp. But if you want to get the value at a, you do star a. And that goes to the address, grabs the number 1, presumably. If you want to change the value of a, you go to that address, you follow the treasure map to the other mailbox, and you set it equal to whatever's at the value of b. You go to b as well. Last line, you go to b now and change it to be whatever the temporary variable was, which happened to be the same as a. So that's where the final value gets swapped. But here, there's a lot more like crisscrossing metaphorically across the stage where you're going to all of these different addresses in the swap function to make these changes. So if we advance now to the pictorial version of this, here's the same story as before with main. And x and y are 1 and 2 respectively. When swap gets called now, notice, and I'll do it with arrows here, a is effectively pointing to x, b is effectively pointing to y. If we really get into the weeds, these are actually like addresses, but who cares about the specifics? It's really just the concept here. So now what happens? Int temp gets star a. Star a means start at a and go there. Follow the arrow, if you will, sort of chutes and ladders style. And then that's 1, so we put 1 in temp. All right, star a equals star b. So let's do it from right to left. Star b means follow the arrow. It's 2. And then what do? Follow the arrow. It's now 2 because you copy 1 to the other from right to left. And then lastly, star b gets temp. So start at b, go to b, and now store whatever the value is in temp. So just by having this basic new syntax of like ampersands and stars and so forth, we can actually now go to places and circumvent what is otherwise a feature of C, that these variables are locally scoped, but you can still access things in other functions as well. So thank you so much for helping step through this. So we now have an application of this that explains why now in this version of the C code, this would actually now work. So in fact, let me go back to my swap code here. And let me change the function ever so slightly in VS Code. So let me scroll down, leaving main the same. And let me change swap's prototype to taking in addresses. Let me go to A here. Let me go to A here. Let me go to B here. And let me go to B here as well. But nothing else changes. This change here in particular is enough of a clue to see that means when you call swap and pass in 2 values, I'm expecting addresses now, not integers. But now that I've made this change, I do need to go up to main and make one change. Does anyone have the intuition for what now needs change in main so that I pass in x and y by reference, that is by address rather than by value or copy? One second. Any intuition for what needs to change in main? Oh, yeah, in back? So close. So on the swap line, it's not star that I want in front of the x and the y. It's instead, what's the other one? It's the ampersand. Why? Because if I want to enable swap to go somewhere, just like Carter and I played this game with the mailboxes, I need to inform swap of the address of x and the address of y. And again, per the beginning of today's class, ampersand is the syntax via which we do that. So I add an ampersand here to get the address of x, ampersand here to get the address of y. And now this code lines up with the picture that Carter just helped us walk through. And so when I run make swap here, I have a mistake. Oh, what did I do wrong? Not intentional, but I guess worth pointing out. I screwed up here. It doesn't like ampersand x because of something on line 3, which is way early in the code. What did I screw up? Yeah, in the middle? Yeah, so this is why you should not copy paste, even though it's necessary for things like function prototypes. If I change swap at the bottom, I need to change its prototype. So let me add the star there, or just recopy paste it at the top of the file. Now let me do make swap again. Let me now do /swap, and I should now see x is 1, y is 2, and hopefully x is 2, y is 1. Which I now do. So the logic is the same. The algorithm is the same. All the week 0 stuff is the same, except now in week 4, you just have a bit more expressiveness via which you can tell the computer exactly what you want to manipulate and how. Any questions then on this technique here? No? All right. Well, when we fix this, there's still going to be problems. And just so you've seen some terms of art here, this is bad whenever you have two arrows pointing at one another. Certainly if you might use and reuse more and more memory. And it turns out there's some terms of art that might suddenly now make sense, especially if you've programmed before. Bad things can happen by this design, but there's really only this kind of design because it's a finite amount of memory. So at some point, bad things are going to happen no matter what if a computer runs out of memory. So it's not that this was a poor decision. It's just sort of a necessary one given finite amounts of memory in a computer. But a heap overflow, so to speak, is whenever you call malloc or similar functions so many times that you just run out of heap space. And the heap somehow clobbers, that is, overwrites or touches the stack part of the computer's memory. By contrast, Stack Overflow, and some of you know this website if you've used it before from other programming classes, Stack Overflow is the opposite. When you call too many functions or you recurse accidentally infinitely many times such that the stack overflows as well. And in both cases, can bad things, heap overflow, stack overflow. I described this incorrectly. So heap overflow is when you actually overflow the heap and touch memory that you shouldn't up there. Stack overflow is when you somehow overflow the stack and touch memory that you shouldn't down there. So with that said, these are really just problems that can happen, and they're specific incarnations of what are generally called buffer overflows. A buffer, like in the YouTube sense, is just like a chunk of memory that in the case of YouTube stores like the next few seconds or minutes of video. But generally speaking, a buffer is just a chunk of memory that the computer is using for some purpose, be it the stack, be it the heap, be it an array in the computer. And so buffer overflows are what happens when you just have logical bugs in your code. But with these primitives now in mind, we wanted to conclude with the final revelations. And that's how some functions like these here work. The other thing in the cs50 library, besides the typedef for quote-unquote string, is, of course, all of these functions. And we give you these functions because, honestly, in C, it is hard, it's annoying, it's painful, it's difficult to get user input correctly. It's very easy when you don't know how much the human's going to type to write buggy code when it comes to it. And indeed, it's really hard to store it correctly without accidentally having some kind of buffer overflow. So for instance, let me show you a program here that I wrote in advance called, let's say, give me 1 second and I'll pull it up. Nope, I'm going to go ahead and write this one from scratch. So let me go ahead and open a file called get.c, wherein I'm going to go ahead and mimic the idea of getting integers manually without the cs50 library. So I'm going to include standard io.h only. I'm going to define main as not taking any command line arguments. And then I'm going to do something like this. Give me a variable x with no value yet. And normally, I would do something like getInt, but let me take that away. No more training wheels for getInt either. So let me just define the int x. Let me then just print out something like a prompt. And I'll just do x colon just to make it obvious to the human what we're waiting for. And now I'm going to use a built-in C function to get user input. I'm going to call a function called scanf, which sort of scans the user's keyboard for input. I'm going to scan it for an integer. So just like printf, I'm going to use %i because I expect an int. And then I want to tell scanf where to put the human's integer from the keyboard. It is not correct, though, to say x, Because if I say x, I run into the same swap problem. Scanf, no function, can change the value of x unless I pass it not by value, but by reference. So we're back to our ampersand friend. And now it has like a treasure map to the actual location of x and can therefore change it. And so now at the very end of this program, let me do something simple. Like let's just go ahead and print out with printf the value of x using %i as always, plugging in x. Not ampersand x. This is now week 1 stuff. I want to print the actual integer value of x. So the only change here is that instead of using getInt, I'm now using this new function that as of today exists called scanf. So let me go ahead and run get, make get to create this program, /get, and let's go ahead and type in a value for x, 50, enter. And it just works. So it turns out getInt is pretty simple to implement. However, notice what does not work. If I type in cat, for instance, cat gets converted to 0. And meanwhile, getInt, recall, will reprompt the user. If a human does not type an actual integer, you get automatically reprompted. So that's one of the features we, for CS50, added to getInt, just to make your programs more user-friendly. But otherwise, getInt is pretty straightforward to re-implement using scanf. Unfortunately, that's not true for strings. Because how do you know when you write your code what word the human's going to eventually type in, how long their greeting, like hi, is, if their name is David or Carter or anything else? You just don't know in advance how much memory you need. So how might we do this with strings? Well, let me go ahead and declare a string s. Although, you know what? There's no CS50 library, so we do char star s today instead. And that gives me not a string per se, but a pointer that will point presumably to a string. Ideally, I would use this, get string. But again, we've taken that training wheel away. So now that I have a pointer s, suppose I prompt the human for a value for s, just like before. Let me use scanf now and tell the user that I expect to read a string, %s from the keyboard, and store it in s. Now, this is subtle. I don't technically need an ampersand here, even though I did for an int, and I would for a float, and a double, and a long, and a bool, and a char. Why do I not need an ampersand in this story to pass by reference? Because s it's already an address. Again, strings are just special. Strings now are always addresses, so you don't need to additionally add an ampersand here. That's the only subtle difference here. But now if I go ahead and print out at the very end what the value of s is, using %s as before, this program looks like it's almost the same as the int version. But let's do make get. And OK, so this is not good. All right, so it doesn't like an uninitialized value. So let me make it happy. I said earlier to always initialize my variable. So let's initialize it to null so that at least something is there. That's your good default value nowadays. Now if I do /get, now we're good. And let me type in something like cat. OK, cat is not x. Well, let me try another word. Maybe it's just cat is wrong. Dog. OK, let me try David. It just doesn't seem to be working. Moreover, it's printing it as a 0. What logically, though, is the bug here? Scanf worked a moment ago for integers, but it's not working for strings. And it seems to be forgetting cat. It's forgetting dog. It's forgetting david. Why? What's happening here? Think back to our yellow pictures of memory. When I yeah. It might be reading just the null itself because s is being initialized to null. And what step have I forgotten from just like a few minutes ago? What did I not actually request of the computer? Like actual memory to store the cat, the dog, the david, right? There's nowhere have I asked the computer for some amount of memory. And so technically, it might be reading it into some garbage location. And that's really the problem here. S is initialized to null now. And so in fact, it is printing 0 as null. But I'm not seeing any of the other letters because there was nowhere to put them. Cat, dog, david, because I didn't ask for 3 bytes, 4 bytes, 5 bytes, 100 bytes. There's no use of malloc. There's no use of an array. There's no memory allocated for anything other than the pointer itself. And this is where, honestly, life gets hard with scanf. Like, I could solve this problem in a couple of ways. Let me go ahead and do this. Instead of declaring s to be a pointer, let me declare s to actually be an array of 4 chars. And now, let me go ahead and recompile the code. So make get, /get, and I'll type in cat now. That now works. Why? Well, I'm allocating an explicit array of size 4, enough for a 1, 2, 3 letters plus a null character. here's where, to someone's question earlier, it turns out that in some context, you can treat arrays as though they are pointers themselves. C will sort of do the conversion for you. But for now, just assume that S is just an array of size 4. And if you pass it into scanf, that's like a treasure map that leads to those 4 bytes. So scanf can now successfully fill it with CAT, DOG, but let's try this again. Let's type in David. And here, OK, we got lucky, but I technically touched memory that I should not. And in fact, if I typed in a long enough string, and I don't think I could do it very easily, like without typing this thousands or hundreds of times, still OK. But you'll notice that it's forgotten the rest of it now, right? So somewhere we went beyond the boundary of the array, and we just don't have enough storage space for that entire thing. So what do you do in your program? If you don't know how long the person's name or the animal name is going to be, what do? 40? 400, 4,000, 40,000. Like at some point, you have to draw a line in the sand. And that's why like getting user input is so annoying in a language like C. And that's why getString exists. What we do, if you're curious, is we look at the user's input and we take baby steps. We look at it one character at a time. And every time we see another character, we actually call malloc again and say, no, I need more than 1 byte. I need 2. Oh, wait, they typed in 3 letters. I need 3 instead of 2. Oh, I need 4 instead of 2. And we have this crazy loop, essentially, that keeps asking for more and more memory, but by taking baby steps. And honestly, if you all had to do that in week 1, my God, like we couldn't even write hello world anymore. And so that's why these training wheels exist, at least early on. And that's why in higher level languages like in Python, you don't have to do this at all. It just works as you'd expect. So what more can we do? Well, you'll see in problem set 4 this coming week, you'll see that there are, if I open up an example like this, phonebook.c, you'll see that you can manipulate files now that you have a vocabulary for pointers. It's going to be new quickly, but here we have an example of how I have a program using some familiar libraries here. But as I claim in my comment, this saves names and numbers to a CSV file. All of my examples thus far, I type in some words, I type in some names and some phone numbers, and they disappear because we only store them in memory. But if you want to store data in like a CSV file, comma, separated values, which is like a simple spreadsheet, like Excel and Apple Numbers and Google Sheets can open, you can actually do this yourself. So just as a teaser for this week, here on line 9, I'm using a new data type, not a CS50 thing. This is a C thing called file. But if you want to manipulate files, you need to use addresses, that is pointers. So here is me creating a variable called file that's going to point to an actual file on the hard drive, on the server or your Mac or PC. fopen is going to be a new function you'll use that will open a file. And it will return effectively a pointer thereto in memory. The file name I want to open is phonebook.csv. And in this example, it's going to be append mode. It will keep allowing me to add more and more names and numbers to this file. Here's some old getString stuff, because I'm not going to reinvent getString with scanf. But down here is a slightly new function. It's not printf, but fprintf. And it turns out it's very easy to print things not to the screen, but to a file with fprintf. And it takes an additional argument. Instead of starting with the quoted string, you'll have to like say what file you want to write to. And fprintf will figure out how to get the bits into that file, passing in something like name, comma, number. So if I run this somewhat quickly here, let me do this. Let me pre-create a file called phonebook.csv. And in phonebook.csv, I'm going to create a temporary row here, name, comma, number, just so that there's something in this file. And now let me go ahead and do this and split my screen here. If I have phonebook.csv on the right and phonebook.c on the left, let me compile, make phonebook, which is the C version, /phonebook. And now I'm prompted for a name and a number. So I'll type in David. And then, for instance, +1, 949, 468, 2750. Enter. Oh, damn it. Bug. Pretend that didn't happen. I forgot to hit enter in the file. So let's do this again. If I run the program again, David, and +1, 949, 468, 2750, enter, it's been saved now to the file. And if I close this file and I reopen code of phonebook.csv, you'll see that the file is persisting. And if I downloaded this to my Mac or my PC, I could double click the CSV file and voila, Excel would open up, or Apple Numbers or the like. And I've actually created an actual CSV file. If you're smiling because I keep repeating my phone number out loud, I would encourage you to call or text that number sometime. It might very well be an Easter egg of sorts. But via these functions here, do we have now the ability to write files, input and output. And among the goals then for this week, as we'll see, are to actually play with images in the spirit of something like Instagram filters or the like. And we'll introduce you, for instance, to a file format called BMPs, which, to come full circle to the start of class, are just maps of bits, but more than just single bits for white and black, but rather colorful patterns as well. And we'll give you images like this of the Weeks Bridge here across the river at Harvard. And you've run, after writing your own code in C and understanding how the data is stored in the computer's memory, you'll be able to apply your own Instagram-like filters to make things grayscale instead, or sepia in this case. You can even flip the bits around so that the thing is a mirror image. You can blur things further, or if you really are feeling more comfortable, you can even write code that finds the edges of the image and creates works of art like these. So all that and more in problem set 4. We will see you next time.